Welcome to a lesson with Dr. Powell. Let's take a look at a related rates problem on a triangle. This time we'll be solving for two missing rates. Now, the idea is we're going to get two function equivalences, two equations, function equations, where everything is a function of t, and we're going to be relating them together. Okay, so like A, B, C, alpha, beta, gamma, we can relate those variables together. Particularly, we want to have B and C in both equations. Now, when we do that, when we take a derivative of both equations, thinking of them as being function equivalences, like the equal sign will be like the equivalence of two functions. If two functions are equal, their derivatives will be equal. So we're going to be keeping everything variable in each one, so that it really is a function, and then we'll have an equivalence of functions. Don't plug in anything until the end, because that messes up what we're really doing with this equal sign when we take a derivative, because it's a derivative of functions. You never take a derivative of an equation. You take a derivative of where you're thinking of the equation as being maybe a number or an expression or something like that. You think of them as functions, and this is an equivalence of functions. Different values of t will give you the same thing in both sides, because the outputs are the same for for the respective inputs of t. So just keeping that in mind as we go along here. Okay, but we want two equations, because then we'll give us two derivative equations with two unknowns. So two equations, two unknowns. And these derivative equations, when these guys pop out, how they pop out, they actually pop out during a chain rule event here. And in that sequence of events, we'll actually get two linear equations. Linear equations meaning there's going to be no variables squared or anything we're solving for, just kind of a simple thing like adding and subtracting and dividing by constant numbers is all it will take to solve this system of equations. We need two equations, two unknowns. It can be simple linear equations, and two unknowns there. The unknowns will be things like this. Will actually be dB dt and dC dt. That will be what we'll be solving for. They come out during a chain rule event after we've taken a derivative of two equations. Okay, so we're going to proceed here. Let's get started. That was kind of the schematic for where we're going to be heading. So we need two different equations that relate B and C together. Again, just as in the last video, I'm going to assume no knowledge of law of sines and law of cosines. Why? Well, just to illustrate that you don't really need it. You can just get it from what you see. Okay, so first equation, we need to be able to relate B and C together. Now, I see this right here. If we were to draw this down, make a right triangle on this side and this side, look at my last video to see how I do this. But this side length right here, and we're going to label these angles, alpha, beta, and gamma, as opposite, like so alpha would be up here, this angle up here. Beta would be the angle opposite B, so beta is, squeeze it in right here, beta. And gamma is the angle opposite C, so right here. I'll just write those in right now. This side length right here, thinking about hypotenuse of 3, thinking of on the unit circle, there being like a 1. If that's beta, this would be sine of beta. We're going to use that idea right there. But knowing the hypotenuse is 3, well, actually, remember, I don't want it to be 3. I want it to be a variable. C. That's just instantaneously at the particular moment in time, it will be 3 feet. But we're going to think of everything as being variable right now. These all things can change. Okay, so C, thinking of C. Okay, so C sine beta. So this side length right here, this height of the triangle, one way of thinking about it is C times sine beta. So that's going to be c times sine beta. What's another way of thinking about it? Well, using this triangle right here. So on the unit circle, and I'll draw it this way, I guess. So it'll be a reflected unit circle. If I had a 1 here, sorry, that doesn't, not very straight lines, is it? And maybe I'll just do it the other way. Okay. So right angle, and I have gamma, and this side length, hypotenuse is b. So this would be b sine gamma, actually, because I mean, if it were a 1, it'd be sine, but then I'm I'm expanding it by a factor of b, so I multiply b to the whole to all the sides of the triangle. So b sine gamma would be another way of saying this height right here. So that's my first equation, b sine gamma. Great. So I have one equation, and in this equation, notice that I'm relating the variables b and c. Now when I take a derivative of this function equivalence that I have right here, thinking of everything as a function of t, then via the chain rule, you will get dc dt and db dt popping out, and you'll have one equation with those guys in it. Awesome. And then at that point, after you do that, then you can start plugging in numbers. Okay, so this is equation number 1, say, of function equivalence at least, and that's where we begin. Now we need to get equation 2, since we have 2 unknowns. Equation 2 of function equivalence, and we're going to, okay, so we need to come up with another way, or another relationship we can get on this triangle. Oftentimes, when we want 2 different equations, one way to go about that is by thinking, let's see, we have a B and we have a C. By extending, making kind of a bigger triangle in some way, maybe even like making a, let's just think how the best way to do this is. Yeah, okay, so let me just label the angles here. So that's alpha, that's beta, that's gamma, and why don't we work with, okay, so that might be a good way to go, with this angle being kind of opposite. Yeah, okay. So what we could do is, so maybe which angle do we want to focus on using here? And I guess it doesn't really matter. We have B and C. Maybe I'll just focus on the angle gamma, I guess. So we could take one angle to focus on, like gamma, and then we're going to, again, I guess we're going to use the same right triangle, all right, or the same length, I guess, coming down. But we're going to use this in a different way. All right, so kind of what we're going to do is we're going to say, okay, so what is, so we have 8, but we want to use C in there. Oh, okay, yeah, there we go. So we have, let's think about the sides of this right triangle in a Pythagorean theorem in such a way that uses B and C. So here it was just we're equating sides, but now let's use a Pythagorean theorem. So equating sides, Pythagorean theorem. 2 different equations, okay? Equating sides, Pythagorean theorem thing. Okay, so to do that, let's think about the side lengths of this. We know that this side length here, we could actually get this side length by using C, and we did that before. We labeled it as C sine beta, right? So C sine, so maybe draw the triangle. C sine beta was one way of saying it. Now this other side length over here, let's write it in such a way that we're using, let's see, letting B, okay, that's right, okay. We really just need an equation that relates okay, so c sine beta. So here, c and b. So we could write this side length right here. This is gamma. So, and this is b, right? So we could write this side length as simply b times the cosine of gamma, right? Okay, so b times the cosine of gamma, c times the sine of beta, all right? And Pythagorean theorem time. So this guy squared plus this guy squared will be equal to b squared. Ah, that's equation 2. All right, so c sine beta squared plus b cosine gamma squared is equal to b squared. Okay, these are function equivalences, equations, right? P is a function of t and everything else. So now we can take a derivative of both equations and we'll get our derivative equations. All right, I'll erase this triangle to get it out of the way. And let's see what we can do. All right, so we take, okay, the first one, keeping in mind instantaneously, it looks like A, but I'm not even using A anywhere. Okay. So instantaneously A is a constant, kind of. I mean, at least instantaneously, it's 0. Its derivative is 0. Which means locally, instantaneously, A is behaving like a constant, but we can't really use that in these derivatives because we didn't put A in there, but we weren't interested in what A was in the end, how it was changing, because we're looking at dB dt and dc dt. Okay, so looks like the rest of these things are constants, I believe. Yeah, or not constants, are variables. So equation 1, we will need to use a product rule for that, because beta, c, we're not going to assume that either of those are constants momentarily. They are just what they are. Okay, so c times sine beta. So we can think, okay, dc dt. Take the derivative of the first one, sine beta, using product rule, plus c, because c, we're just not taking derivative of that this time, but then take a derivative of this part, which is the cosine of beta, but the derivative is with respect to t, so then we have to multiply by, so after cosine beta, you multiply by, and you can do that just so you know you're not putting out the input of cosine, d beta dt, because derivative of the inside, you have to multiply by that. So that's the derivative of this part, c times sine beta, is equal to, so the derivative of this function is going to be equal to the derivative of this function. The first part is, derivative of the first part is dB dt sine gamma, again using the product rule, plus b cosine of gamma times d gamma dt, because I used a chain rule there, derivative of sine of gamma, but then multiply by derivative of gamma. Okay, so this would be, this is a, you can say, derivative equation 1. And this relates, look, it relates dc dt and dB dt. And you can plug in, we actually are given the values for d beta dt, d gamma dt, and so forth, but just remember something. And this was as in the last video. These values, they're given in degrees per second. Now I did this on purpose so we can remember something. You have to convert them to radians per second here, because the way we take derivatives of sine and cosine have assumed something. We've assumed we're in radian mode. Otherwise, there'll be some extra constant we'd have to be multiplying by and change what our derivative rule is. So if you want the derivative of sine to be cosine, you better be in radian mode. So you better convert d beta dt and d gamma dt to radians per second. Okay. So, and how do you convert to radians per second if you have degrees? Well, you just convert the amount of degrees to radians, like how many radians is this per second? So what do? Well, you think, well, what fraction is this of 180? So you can compute that. And because that's how many 180s you have, well, we just want to say that's how many pi's we have. So what fraction is of 180, and that's the same fraction it'll be of pi, because in the conversion, pi is the same thing as 180 degrees. So, I mean, this is a simple conversion of this guy right here to radians per second if we need that. All right, when we plug in. In this video, I will not actually do the solving of the two equations. This is just in this video, we just have the setup. So this is derivative equation 1. Now, what about derivative equation 2? Take the derivative of this part with respect to t. So right here, using the chain rule, you have 2 times c sine of beta. Okay, but then we have to so we're using chain rule and power rule. So first, right, so 2 times this, but then the derivative of the inside will have a product rule, right? C sine beta was raised, this was squared. So here we have same thing as we did up here for product rule, and we wrote it right here. So we're going to have, and remember, chain rule in that product rule as well. So dc dt times sine beta plus c cosine of beta, and then d beta dt, which is exactly what I had on this side right there. But that's what we're multiplying to this 2 times c sine beta. All right, so that was just that part. Oh, we don't have enough room here, so I just have to keep on, say, plus. And then this guy right here, again, same idea, 2b cosine of gamma, and we're not using the 80t, so assuming everything's variable. So 2b cosine gamma here, all right, and then times the derivative of b cosine gamma, which is by product rule and chain rule dB dt cosine of gamma plus b, actually there'll be a minus, all right, because derivative of cosine is negative sine, so minus b sine of gamma, and don't forget the d gamma dt by the chain rule. Aha, that's that side. Oh, great. Okay, so this plus this is, I'll put the equal sign down here, maybe, equal, then derivative of this, 2b, but then with chain rule, dB dt. Woof. Okay, notice we have, now this is just a number. We can plug things in now, right? But the only things we can't plug in is what we don't know. We don't know dB dt, and we don't know dc dt. Those are both there, which is great. We know d beta dt after we convert to radians. Remember that? D gamma dt after we convert to radians. And then, we can plug in the b and all these other things. We can plug those guys in, and then we're then we have an equation with 2 unknowns, dc dt and dB dt. In fact, we have 2 equations with these unknowns, dc dt. Everything else we can plug in and get what it is, but dc dt and dB dt. Now, in the end, what happens is this is a number, and it multiplies across this addition. So we just, so as we do that, and as we distribute, and as we collect terms, we subtract over and factor. That's a good thing to review here. Maybe, I mean, it's a little bit messy, but maybe I'll go through it just so we can kind of see how this goes because of this particular factorization that we have. For kicks, what I'll do is I'll just make names to things to make things simpler. This thing right here, like this part right here, I'm just going to call it capital A. Capital A is just that number right here. We're multiplying to this whole set of parentheses. In here, times dc dt, the next number I see, so sine of beta, I'm just going to call b. plus b, or no, not plus b, times b. Sorry. Okay, times b. All right, and then this guy is just a number. We have everything to plug in for that. Let's call it c. So you can plug these things in and get these numbers and then look at it again. But just realize these things are A, B's, and C. I mean, I'm just for it's useful if you just put letters sometimes for things. Then you're not writing all these numbers out all the time. Okay, plus, and then this guy right here, I'm just going to call D times, and then you have dB dt times another number right here. I'll call E, and I'll just say minus f because we see a minus sign. That's fine. And then equaling, and then that's some number I'll just call G times dB dt. So, I mean, this last equation really looks like this after you start plugging things in. dC dt and dB dt are here. All right. Now, keep in mind we can distribute things in. And if we distribute, we have A, B, dC dt, right? So we're just going to get a number like A times B times dC dt, and then A times the C, plus A times C, plus, and then this part is just dE dB dt minus dF is equal to G dB dt. So we have, and then we can collect terms and work on that. Essentially, so this A times C and dF, those are just numbers, and we just put them to the other side. If we do that, we'll have a negative AC plus dF on one side, and the other side we'll have AB dC dt, and then we have this dE plus dE dB dt, and then we subtract that this part over, minus G dB dt. Notice these two terms right here have a common factor of dB dt. So if you only want to see one dB dt, what do? You factor. That's the same thing as adding common like terms. I mean, this is a number, that's a number, you just add the coefficients of dB dt, right? Same idea. So you can factor out the dB dt, dE minus G times dB dt, and if you want, that was just an illustration of how you get dC dt and dB dt, like you have a number times dC dt plus a number times dB dt is equal to a number. So if you've ever seen a linear equation, two unknowns, like with x and y, like say something like ax plus by is equal to c, and something like dx plus ey is equal to f, this is the exact same thing. The difference is that x and y are now dC dt and dB dt. That essentially you can work both equations into this form and then just solve by adding equations, subtracting equations, multiplying equations by things, substituting, whatever you want. There's various ways of doing that, but I'm not going through that in this video. I just wanted to point out, the main point of this video was to just make sure we could get to this point. Can you get there? Can we effectively come up with function equivalences like this from the triangle, and then take derivatives to get derivative equivalences with chain rule stuff popping out, so we can relate our dC dt to dB dt, and do it with keeping things variable. Remember, don't plug in anything until the end, until you have your derivative equations. Thanks for watching.